Hey guys, today we'll be talking about section 2.8, graphing linear and absolute value inequalities. In previous section, we graphed linear equations and absolute value equations. These are going to be very similar. However, remember, one of the main differences between equations and inequalities are there are a lot more solutions in inequalities. And the way that you show those solutions on a coordinate plane is that you shade them. The first step we're going to do is graph the line as if it was an absolute the first thing we're going to do is graph the line as if it was an equation. Notice problems 1, 2, and 3 are all linear inequalities. They don't have equal signs, they have inequality signs, but the way we graph them is as if there are equations. Notice that this number 1 has a y-intercept of 1, so we'll plot that first, and a slope of 3, in which we would rise 3 and run 1. Remember, 3 as a fraction is 3 over 1, representing the rise over run of the line. We'll then go ahead and make a nice straight line. The first thing you have to ask yourself is whether this line is going to be solid or dotted. Are the solutions included on this line or either above or below the line? Well, since it has a less than sign, this is going to be a dotted line. So we could then go ahead and erase to make this a dotted or a dashed line. This is very similar to open circle or closed circle, but now we are on a coordinate plane graphing lines, so we will have a solid line or a dashed line. The next step is then to shade either above or below the line, representing the solutions. One method of doing this is to test a point. The easiest point on the coordinate plane to test is 0, 0. If 0, 0 is a solution, then all the ordered pairs of that line is also a solution. If it's not, then the solutions are on the opposite side of the line. How are we going to test that ordered pair? Well, our original inequality is y is less than 3x plus 1. So if we plug 0 in for y and x and simplify, we would end up with 0 is less than 1. We have to ask ourselves, is this true? Is 0 less than 1? Yes, it is. Therefore, 0, 0 is a solution. And therefore, the solutions will be on this side of the line. All of the ordered pairs that we are shading right now are representing solutions to that inequality. If I substitute any ordered pair on that side of the equation, we would get a true statement as we did with 0, 0. If we substitute an ordered pair on the other side of the line, we would get an untrue statement showing that those are not solutions. All the ordered pairs in the shaded region are solutions, however, not the ones on the line. On number 2, notice that we have a greater than or equal to sign. So this line would be a solid line. It's already in slope-intercept form for us, so we'll start at -5 on the y-axis, and then use the slope of 1 to graph our second point. A slope of 1 will tell us to rise 1 and run 1 on the coordinate plane, in which this would be our line. Again, it is a solid line because we have a greater than or equal to sign. Every ordered pair on this line is a solution to that inequality. Let's now find where else the solutions are, either above the line or below the line. Let's go ahead and test a point, and again, just like number 1, 0, 0 is the easiest ordered pair to test. So if I were to substitute 0, 0 into our original inequality, we would get 0 is greater than or equal to 0 minus 5, or 0 is greater than or equal to -5. Is this statement true? Is 0 greater than -5? Yes, it is. Therefore, this ordered pair that we just tested is a solution. In fact, that also means every ordered pair on that side of the line are also solutions. So that would be the side that we shade. The solutions to the inequality are all the ordered pairs in this shaded region and all the ordered pairs on the line. Number 3, Very similar. We're going to graph a dotted line because we have a greater than sign showing that the ordered pairs on the line we're going to graph are not solutions. Since this is not in slope-intercept form, what we're going to do is first put it into slope-intercept form by subtracting 4x on both sides to get y is greater than negative 4x minus 1. This new inequality, now that it's in slope-intercept form, I know has a y-intercept of negative 1 and a slope of negative 4, in which from that first point we will go down 4 and right 1. And again, this is going to be a dotted or a dashed line. You could either graph it as a dashed line if you're doing this by hand. I'll just erase parts to show that it is a dotted line. What this means is that all the ordered pairs on the line are not solutions. Where are the ordered pairs that are solutions for this inequality? Either to the left or to the right of this line. Let's go ahead and test a point to see where the solutions are. Let's test 0, 0 for the mere fact that the ordered pair 0, 0 is just easy to simplify once substituting into the inequality. What you're going to want to do is substitute into our original inequality, 4x plus y is greater than 1. We would get 4 times 0 plus 0 is greater than negative 1, or 0 is greater than negative 1. Ask yourself, is this true? Is 0 greater than negative 1? Yes, it is. Therefore, this point that we just tested is a solution. Not only is that point a solution, but also all the ordered pairs on that same side. So we will lightly shade, if you're using a pencil, this is just a light shading, all the ordered pairs on the right side, showing that all of those ordered pairs are solutions to the inequality. What does that mean? You could take any of those ordered pairs, substitute it into the inequality, and we would end up with a true statement. Our next three problems, as you can see, are all absolute value inequalities. So what we're going to do is graph the absolute value equation and then shade either inside or outside the absolute value graph to show where the solutions are. We are going to use our translations that we learned a couple of sections ago, showing that that V shape is going to be moving up 1 unit. This is going to be a solid V, just like the lines above. If it was a less than sign or a greater than sign, we would be graphing a dotted or dashed V. But since we have a greater than or equal to sign, we're going to graph a solid V. The solid V means that all the ordered pairs on this graph, if substituted into the inequality, will be solutions or will have a true statement at the end. Let's test where the other solutions are. Again, we could test 0, 0 by plugging in to our original inequality. Y is greater than or equal to the absolute value of x plus 1. If I substitute 0, 0 in, we'd have 0 is greater than or equal to the absolute value of 0 plus 1, or 0 is greater than or equal to 1. Ask yourselves, is this true? Is 0 greater than 1? No, it's not. Therefore, the point that we just tested is not a solution. In addition, nor are all the ordered pairs on that side of the line or of the graph. So we're not going to shade outside that V or outside the graph. We are going to shade inside. This is representing that all the ordered pairs inside the V are solutions to the absolute value inequality. If I substitute any of those ordered pairs into our original inequality, we would end up with a true statement, unlike we ended up with a false statement when plugging in 0, 0. Notice 0, 0 is not shaded, it is not a solution. Let's take a look at number 5. Similarly to number 3, this is not in the correct form that we graph absolute value graphs. It's kind of like putting it in slope-intercept form such that we want to simplify for y. So if I were to subtract the absolute value of x on both sides our new equation or our new inequality would be y is greater than or equal to negative absolute value of x plus 4. This means that the translations would move that V shape up 4 units and be graphed upside down. Since it is a greater than or equal to sign, it's going to be a solid line. Let's now check to see, since this is an inequality, where all the other solutions are. All of the ordered pairs on the graph are solutions, plus either all the ordered pairs above the V shape or inside and below the V shape. Again, let's test 0, 0, since that's at the easiest point to test. And when we substitute it into our original inequality, we'd get the absolute value of 0 plus 0 is greater than or equal to 4. Since 0 is not greater than or equal to 4, this is a false statement, and 0, 0 is not a solution. Therefore, we tested this point, and it's not a solution. Therefore, none of the ordered pairs in that area are solutions either. So we're not going to shade inside the V shape or the graph. We are going to shade outside, showing that the solutions are above or outside the V shape, along with all the ordered pairs on that V shape. Lastly, our last problem is already in the correct form for us to graph. However, it has a less than sign, so we will be graphing a dotted or dashed V shape. It's going to be going down 3 units and upside down. So we will get this graph here, and again, it's going to be dotted or dashed, like so. And then let's find the solutions. The ordered pairs on that graph are not solutions. Therefore, when you substitute them in, you will get a false statement. Let's see where the solutions are by testing our ordered pair 0, 0. If that is a solution, then we'll shade above. If it's not, then we will shade below. So we're going to ask ourselves, is 0 less than negative absolute value of 0 minus 3? Or is 0 less than negative 4? 0 happens to be greater than negative 4, therefore the ordered pair that we just tested is not a solution. So we're not going to shade in that area or above the graph, we are going to shade below the graph. The ordered pairs that are solutions to this inequality are not on the line or on the V, but yet inside and below. So that is the difference between linear inequalities and absolute value inequalities. And the second page, what we're going to do is just do the opposite and write the equation. So I'm going to do the first two and then leave the second two for you guys to try. The first problem has a horizontal line, so I know that that would be a slope of 0 and crosses the y-axis at 2. So that equation would be y equals 2. However, we know that we have an inequality, and the first thing we know is that the inequality is going to be either a less than sign or a greater than sign because we have a dotted line. Since it's shaded below, we know we have a less than sign, and this would be our inequality for our first graph. We could also double check to see if our sign is correct by plugging a solution in. For example, 0, 0 is a solution because it's in the shaded area. If I plug in 0 for y, we would get 0 is less than 2. That would be a true statement, meaning that that ordered pair is in fact a solution. If we plugged in any ordered pair above the line that's not in the shaded region, it should not be a solution, therefore it would come out with a false statement. The one next to it is an absolute value function, since we have that V shape. So we know we're going to have absolute value lines, and our sign is going to be either less than or equal to or greater than or equal to, because it's a solid shape. It's a solid graph with solid lines. Since they shaded under, a quick way to know what sign is going to be, it would be less than or equal to, since it's under, and a solid V. Lastly, we're just going to use our translations to write our the rest of the inequality. That would be the absolute value of x. It moved to the left 1 unit, so that would be 1, and it moved down 2 units, so we would write -2 at the end. What I'm going to do is leave the last two for you guys to try. Pause the video. Once you get your answer, play the video for an explanation. Here are the two graphs on the bottom. This first one here is a line, so I know I'm going to write the equation in slope-intercept form. It has a y-intercept of 1 and a slope of 1/2. If you couldn't find the slope by doing rise over run, you could always take 2 points and put it in the slope formula. I know it's a greater than or equal to sign because it is a solid line and the shading is above it. And the second problem is going to be an absolute value inequality. It's going to be a less than sign because, first of all, it is a dotted or dashed absolute value graph, and the shading is below or inside the absolute value, so that's why it would be a less than. It is a negative on the outside since it's upside down, and it moved down 3 units, so we would put the -3 at the end. Please let me know if you guys have any questions on this lesson, and I'll talk to you soon.